This is an explanation of the subgraph isomorphism problem. Given two graphs G1 and G2, determine whether any subgraph of G1 is isomorphic to G2. And isomorphic is defined as two graphs are isomorphic if a relabeling of the vertices in one makes the relabeled graph identical to the other. So to define isomorphism, isomorphism means that two graphs are identical. So the two graphs in this case are GA and GB. So every vertex in GA has an equivalent vertex in GB where they share the same edges, and in this case they look alike, although it's important to note that they don't necessarily have to be drawn the same way with the same angles. As long as there is a vertex that's mapped according to the two graphs, and there's also the edges that are shown correctly, and they're all equivalent, then the two graphs are isomorphic. So we can see here that GA and GB are isomorphic according to the relabeling scheme 1 to 6, 2 to 9, 3 to 7, 4 to 10, and 5 to 8. And there's a number of different relabeling schemes for this example, but if there were no relabeling schemes, that would mean that they are not isomorphic. So you need at least one relabeling scheme to show that two graphs are isomorphic. And this is just an example of two graphs that are not isomorphic. So you can see with GA and GB, no matter how you relabel the graphs in GA, you cannot get an identical graph of GB because you can see there's a different number of edges. So that's something you can observe, that for two graphs to be identical, they have to have the same number of vertices and the same number of edges. And in this case, they don't. And the idea with the definition of isomorphism is that because there's no relabeling of the vertices in GA, it cannot possibly be isomorphic to GB. To define a subgraph G' of G contains a subset of the vertices in G and their corresponding edges. So in this example we have G with the vertices labeled 1, 2, 3, 4, and 5, and to choose any subgraph of that would be to choose a subset of the vertices and to include their corresponding edges. So G' is an example of a subgraph of G because we're choosing the vertices 2, 3, and 4, and there's the edges between them. So there's the edge between 2 and 3 and the edge between 3 and 4. There's no edge between 2 and 4, so we don't include that. And that's what a subgraph is that you're just choosing a subset of the vertices and adding the edges that are included between them. So having defined what an isomorphism is and what a subgraph is, we'll return to the definition of the problem. Given two graphs G1 and G2, determine whether any subgraph of G1 is isomorphic to G2. So in other words, whether any subset graph of G1 is identical to G2. So that means that there are many different possibilities to this. And that's why this is a combinatorial optimization problem. So the prompt is to determine if G1 has a subgraph that is isomorphic to G2. And the possibilities that could be checked would be every subgraph of G1 and every possible relabeling of that subgraph. Because for every single subgraph that G1 has, we have to check if that is isomorphic to G2. So you can see in the example below that G1 does in fact have a subgraph that is isomorphic to G2. Now G1 itself is not isomorphic to G2, and you can see that pretty simply just by looking at the number of vertices and the number of edges. But if we go through all the different possible subgraphs and then we check, is there a possible relabeling of that subgraph to G2? It turns out that in fact there is, and the scheme is right there. It's 1 to 7, 4 to 8, and 5 to 6. And as with other examples of isomorphisms, there may be more than one relabeling that is valid. And the answer to the question to the subgraph isomorphism problem here is yes. G1 does have a subgraph that is isomorphic to G2, because that's the question that we're answering. So because the subgraph isomorphism problem is a combinatorial optimization problem, we can describe it both as an optimization version and as a decision version. So for the optimization version we have three conditions: a set of states or candidate solutions, a cost function, and the goal is to find the state with the lowest cost. So we can look at the different states because there's the set of all unique subgraphs of G1. So G1 can have many different subgraphs, but there may only be one, or perhaps more than one, but there may only be one subgraph of G1 that is isomorphic to G2. So those are the different candidate solutions. And the cost function in this case is quite simple because we're just looking for a yes or no answer. So the cost would be 0 if the state is isomorphic to G2, if the subgraph is isomorphic to G2, and it would be 1 if the subgraph is not isomorphic to G2. And that's because we're looking for the states where it is isomorphic, we're looking for the low cost states, we're looking for the states where the cost is 0. So those would be the solution states. And quick note, checking for an isomorphism between two graphs in itself has a set of candidate solutions, which is the possible relabeling of those vertices. So not only are we looking for the unique subgraphs, but we also have to check, okay, what is the possible relabeling that makes it isomorphic to G2? So for the decision version of the problem, given an input, the output is either a yes or a no. So because we're looking for if there exists any possible subgraph that is isomorphic to G2, then it is a yes or no question. All we care about is there at least one subgraph that is isomorphic to G2? So the question would be, given two graphs G1 and G2, does there exist a subgraph of G1 that is isomorphic to G2?
Next, we will go through a simple explanation with a clear and concise example of how one graph can have a subgraph that is isomorphic to another. Now, looking at example G1 and G2 for our graphs, we're going to have G1 represented as 1, 2, 3, 4, 5, and 11, and G2 represented as 6, 7, and 8. Now, the numbers don't really matter and carry no weight. They're just easier for us to keep track of and show how 3 points in G1 can be subgraph isomorphic to G2. Now, how to go through this with the algorithm is by first looking at G2. Let's take point 6 for example. Point 6 has to have a candidate that is 2 degrees or greater in G1. Essentially what this means is when we look at G1, we have to find all the points in there that are potential candidates to replace 6. And but the way we check this is if any of these points have the same degree or greater than 6 in G2. So for example, point 1, point 2, point 3, point 4, and point 5 all have degrees of 2 or greater. That way we can add them to a candidate list below. Once we go through the candidates for 6, we should look at 7 and 8. But because 7 and 8 have the same exact degrees as 6, we can clearly represent all candidates for 6, 7, and 8 as the same numbers, being 1, 2, 3, 4, and 5. Now what we'll do with 6 is we'll start looking through the list and say, for example, we pick the number 4. Now 4 has a degree of 2, which obviously makes it a candidate, but when we look at point 11 that's attached to point 4, we see that 11 has no degrees to it. This is where we can begin to refine our search a little bit. So essentially we get rid of the number 4 as a potential candidate in 6, 7, and 8 because 11 has no degrees leading away from it, and as we can see from the representation of G2, all points must have at least a degree of 2. Now because 11 only has a degree of 1, we get rid of 4 as a potential candidate for all points in 6, 7, and 8's list. So let's say we land on the number 2 next for our search. 2 is a potential candidate in 6, and we look around and we see that all of the other nodes all the other points that it's surrounded by are also potentials to keep this subgraph going together. So let's say we select 2 as our first potential for our subgraph. Now we go to one of the neighbors of 6 to keep continuing this. So from 6 we can move to 7, and from 7 we say a degree of 2, but now when we look at the candidate list for 7, we've already gotten rid of 4 as it's been refined by our search, and we get rid of 2 as we're on point 2. So 2 can't be the potential again for replacing point 7 in the subgraph. Now what we see from here is that we have the potential of having 1, 3, or 5 as our next point on the subgraph, and as we can see from all these points represented in G1 that they're all potentials to complete the subgraph that is isomorphic to G2. So let's say, for example, we take point number 1 as a potential replacement for 7. So we select that, and now all we have to do is go to the neighbor of 7 and complete the subgraph isomorphism and see if it's possible using these potential candidates. In 8, we've already refined 4. We've already gotten rid of 2 as we've already visited it, and we can now get rid of 1 as 1 is the place that we're at currently. Now from here we have 3 and 5. We can't get to 5, so obviously that eliminates 5, and 3 is our last example potential point, and we select 3, and that completes our subgraph isomorphism. So we can see that in G1, points 1, 2, and 3 create a graph that is a subgraph of G1 that is exactly isomorphic to G.
These are the graphs we will be using for the next example. G1, if rearranged, can be set up to look like a tree. This intuitively means that no subgraph of G1 can be isomorphic to G2. First, we set the candidates for A and the candidates for B to be 2, 3, 4, 6, and 7. The candidate for D is 3, and the candidates for C are all vertices of G1. We will start by refining the candidates of C. First, we'll set 1 to be C. If this is the case, then that means D has to contain 2. However, it does not. It contains 3. Therefore, we remove 1 from the candidates of C. At this point, it should be clear that the only candidates for C have to have 3 as a neighbor. Therefore, the candidates of C must be 2, 4, and 6. If we continue to refine this way, then at the end, the candidates of A, B, and C will all be 2, 4, and 6. Now, we will test the graph for isomorphism. We set the candidates of A to be 2, and then remove that from the candidates of B and C. One neighbor of 2 is 3, which is in candidates D. This works. However, the candidates of B, 4, and 6 are not neighbors of 2. Therefore, this does not work. By setting the candidates of A to 4 and to 6, we get the same results. Neither 2 and 6 can be a neighbor to 4, and neither 2 or 4 can be a neighbor to 6. Since no vertices can be mapped to A, this means that this subgraph is not isomorphic to G2.
You used to call me on my cell phone, late night when you need me.